It's great to be here with Rocio and Matias talking about the synthetic controls and the regression discontinuity design. And yes, and the first lecture is going to be about the synthetic controls, so let's go for it. So synthetic controls were originally developed to estimate the effects of large aggregate events, and in particular, the effects of policy interventions that are deployed at the aggregate level, interventions that may affect entire cities or regions or countries. If you think about that, much of the available machinery that we have in economics and in statistics to estimate treatment effects is designed with the idea of estimating an average treatment effect over some population, and from that population we have extracted a large sample of individuals. Some of them are treated, some of them are not treated, and we are going to compare them in some way. However, like many of the policy interventions that we care about, or many of the aggregate events that we care about, well, they are not like that. They do not happen at the individual level. They happen at the level of large jurisdictions, as I said before, like cities, regions, or countries. And even if you are in an experimental setting where the experimenter has the freedom of, deploying the intervention at a micro level or at a macro level or at an aggregate level, the experimenter may not want to do it at the micro level because, there may be like a fairness considerations. For example, if you have two individuals in the same location and one is treated and the other is not treated, this could raise like issues of fairness. And also you may have like interference issues. You may have like two individuals in the same locations, one is treated and one is not treated, but they are interacting, and this is creating a bias in the experimental estimate. So to avoid all these type of issues, you may want to implement your intervention, not at the micro level, but at the level of a city or a school district or a region. Synthetic controls have been applied to study a variety of problems empirically, from immigration policy to the effect of corporate political connections. They have been adopted as the main tool for data analysis, across different sites of issues in prominent policy debates on, like immigration and minimum wages. And they are also applied to outside economics, in the social sciences, in biomedical disciplines, especially in epidemiology, in computer science, and so on. They have also been widely adopted by multilateral organizations, think tanks like business analytics units, etc. And for example, a synthetic control method plays like a big role in the official evaluation of a massive educational program funded by the Gates Foundation. And then, while I think it is fair to say that the econometrics methods are not a daily staple of the popular press, and I guess this is a huge understatement, synthetic controls methods and their application have at times managed to capture the attention of journalists and of the general public. So what is my goal for the talk today? So I want to provide an introduction to synthetic control methods, describe some of the advantages of this methodology, which in my mind is explain the popularity that I have described before. And I also want to talk about some recent developments like in synthetic control estimation. And I will finish with some remarks about potential avenues for future research. So that's what I'm going to that's going to be the next 50 minutes. Okay. Something that I should say is that many people have contributed to our understandings of synthetic control methods and related methods, like I don't know, in economics, like Hidde Invens, Victor Chernuchov, Bruno Furman, Jesse Rostein and co-authors, and in statistics, Avi Feller, David Blay and co-authors. In computer science, you have Deva Brasa and all his group in MIT. And the literature is very large, and I won't have time to cover all this, and I will basically going to concentrate in the original formulation of synthetic controls, although there are many important extensions, many important related methods that are out there in the literature, and of course there are many empirical applications that I will not be able to cover. Okay, so let's start about what synthetic controls are about. Synthetic controls are based on the observation that when you have, as I described before, a few aggregate units are the units of the analysis, then a combination of comparison units, what we are going to call a synthetic control, is often going to do a better job reproducing the characteristics of the treated unit than any single comparison unit alone. Okay, and motivated by this consideration, a synthetic control is going to be selected as the weighted average of all potential comparison units, but we are going to choose this average in a way that best resembles the characteristics of the treated unit. And when I say characteristic of the treated units, I'm thinking about, like predictors of the outcome of interest. You will see in a moment. Okay, so like to formalize these concepts, let's introduce some notation. Suppose that we have like a j plus 1 units, t periods without loss of generality. Unit 1 is exposed to the intervention of interest after period t0, and you have like the remaining j units that are untreated, and this is what we are going to say they are an untreated reservoir of potential controls. We will call them the donor pool. This is the set from which we are going to choose our potential comparison. Okay, or the comparison for the treated unit. And this is going to be a framework of potential outcomes, like we will have YIIT and YNIT. These are going to be the outcomes that will be observed for unit I at time t with and without the intervention, respectively. And what we aim to estimate the effect of the intervention on the treated unit in a post-intervention period, and this is going to be, of course, as always, the comparison between the two potential outcomes. The first one is easy. With that one we observe. We don't have to estimate anything there. But the second one is complicated, and all our effort is going to be concentrated in estimating this second object. So as I said before, a synthetic control is going to be a weighted average. So each potential synthetic control can be represented by a vector of weights. Okay, one weight for each unit in the donor pool. And all the weights are going to be like a non-negative, and they are going to sum to 1. And we do that to avoid extrapolation, although this restriction could be relaxed. And in fact, they have been relaxed in the literature. Okay, so how are we going to choose among all these like potential synthetic controls? Well, we are going to, specify a vector of characteristics for the treated units, and again, these are predictors of the outcome variable of interest. This is a k times 1 vector, and we are going to have a matrix with the same values for the same characteristics for the units in the donor pool. And our vector of synthetic control weights is going to be chosen to minimize the discrepancy between x1, the characteristics of the treated unit, and x0w, the characteristics of the synthetic control, like subject to the weight constraints that we have that we described before. Okay, and now once we have this W star, like the estimation of the treatment effect in the synthetic control framework is easy. Like your estimate is going to be just the outcome for the treated unit and minus the outcome for the synthetic control. And this comparison, you can do it period by period, after the intervention. Okay. In the previous slide, I used a norm, but I did not define it. And in fact, there is a lot of flexibility in what you can use there. But most people use like some type of weighted Euclidean norm, in which these weights here, these constants, are going to reflect the predicted power of each of the predictors. And these constants, V1 to Vk, that are these weights for each of the predictors, can be chosen by the analyst directly, or can be chosen in a data-driven way. So let's look at the first application of a synthetic control estimation. This is an application to the effects of the German reunification on GDP per capita in West Germany. So what we see in the figure on the left-hand side is the series of GDP per capita for West Germany before and after the reunification in 1990. And we also see the same series for a sample of OECD countries. And something that you notice here, like almost immediately, is that here we don't have the usual conditions that we want to have to apply something like difference in differences. We don't have parallel trends. In fact, the trends before the German reunification for West Germany and for other countries in the OECD are quite different. However, what the figure on the right-hand side shows is that there is a combination of countries in the OECD that very well reproduces the trajectory of GDP per capita for West Germany before the reunification. And as we will see later, it is also going to reproduce other characteristics, other predictor of the outcomes for West Germany. Okay, so like you can see, the match is is very, very close. And I guess that some of you may be thinking like, okay, I know what these guys did. They put all the values to get the fit that good. You probably put all the values of the outcome variable in the pre-intervention period. You put all of them into X1, okay, in order to have this fit. And in fact, we didn't do that. We did something very different. We just took, the average over 10 years before the intervention, and that's what we put in the X1, okay, and then like other predictors, okay, but you can see when you fit this average, you fit the whole trajectory very well. And why is that? Well, if you look at the raw data, you can see that there are some countries in this sample that they are co-moving very nicely. They are co-moving very strongly, and this co-movement between countries is exactly what the synthetic control is trying to exploit, and that's why we can fit this series, quite well. Okay, so what is X1 in this case? So we have here X1. These are like predictors of economic growth that are typically used in the literature, and these are the values that we observe for West Germany, and these are the values here that we observe for the OECD sample. And you can see that West Germany is not very close to the average of the OECD sample, even when we are already using a sample of industrialized countries. Okay, but however, what we can see also in the second column is that there is a combination, there is a convex combination, a weighted average of all these countries in the OECD that very, very closely reproduces the characteristics of West Germany. Okay, and this is going to be our synthetic control. This is going to be the comparison that we are going to use. And if you are thinking about, so what is this synthetic control for this problem? So here we have like perhaps not very surprisingly, Austria carries a large weight. Also like Japan, the Netherlands, Switzerland, and the United States, they carry positive weights, and the rest of the countries have 0 weights. Okay, so like as you can see, this synthetic control is sparse. This is something that is typical of synthetic controls, and we will see why later, and which makes the interpretation of synthetic controls particularly easy. Okay, so what are the properties of these estimators? One could ask. To establish the properties of the estimator, we are going to adopt some type of, benchmark model for the, like a benchmark model, generative, some model that is going to generate the outcomes, okay, of interest. And by the way, this is only the potential outcome without the treatment. As I said before, the outcome with treatment I observe. So, I don't have to, I don't have to assume anything about it. My only assumptions are going to be about what happens without the treatment. And in this simple linear factor model in which the outcome is going to depend on characteristics of the units that we observe and characteristics of the units that we don't observe. And they come with coefficients that vary with time arbitrarily. And also we have like an individual transitory shock epsilon that we are going to model as random noise. And suppose that we can choose W star such that we can reproduce the characteristics of the treated unit, and also we can reproduce the trajectory of the outcome for the treated unit before the intervention. Suppose in fact that we can do that for any value of epsilon. And in practice, this restriction may only hold approximately. Then we can establish a bound on on the bias of the synthetic control estimator. And here is for completeness, I have here like all the elements of the bound, and like is this a complicated object, but I only want to focus on something that we have here inside this max. We have these ratios, and these ratios are these two objects, and these two objects are related to the scale of the transitory shocks epsilon. And in the denominator, we have like functions of the T0, that is the number of pre-intervention periods. And remember that, to get this bound, we need this to happen, okay? Fine. So what are the implications of all this? What are the implications of this bound of the bias? Well, the first thing that we have to remember, again, is that this bound is predicated on close fit. And it is controlled by the ratio between the scale of the transitory shocks and the number of pre-intervention periods. That means that the credibility of synthetic control is going to depend on the extent to which you can approximate the trajectory of the outcome variable for the treated unit for an extended pre-intervention period. So T0 has to be large. The variance of epsilon cannot be very large. Otherwise, you're not going to be able to fit this trajectory. There are no ex-ante guarantees on the fit. Like sometimes you are able to fit, sometimes the unit may be very extreme and you are not able to fit. And if the fit is poor, like we will recommend against using the synthetic controls, or at least against using the, this vanilla version of the synthetic controls. There are some things that you can do about it, like bias correction, that I won't have time to discuss today. Okay. We have to be aware that, settings perhaps with a small number of pre-intervention periods, large number of units in the norm pool, and large noise, like a large variance of epsilon, they create substantial risk of overfitting, in the sense that you are not fitting the outcomes because the characteristics of the units, the Ci and the mu I, are similar. You are fitting the outcomes because like you have enough variation in the epsilons, and from this variation in the epsilons, you can fit. You give me enough noise, and I can fit anything. Okay, so to reduce so what we are going to do in this setting, I think like one good piece of advice is to restrict the donor pool to units that are similar to the treated unit. As we did for the German reunification example, we look only at countries in the OECD. For example, you wouldn't want to fit a country that like a middle income country with a country that is like a very rich, and a country that is very poor, because that will create interpolation biases. But also you may be aware of the risk of overfitting, and having like a lot of units in the donor pool. You may be risking doing some overfitting, and therefore having some bias. So what about inference inference in this setting? Like inference for the synthetic control method is complicated by the fact that we are estimating the treatment effect typically for one unit. So standard asymptotic tools do not apply in this context. And to address this problem, we are going to base our inference on permutation methods. So basically what we are going to do is we are going to create a permutation distribution by iteratively reassigning the treatment to all the units in the donor pool, and estimating these placebo effects in each iteration. And then the effect of the treatment on the unit that is affected by the intervention, we're going to say that this effect is significant when the magnitude of the estimated effect is extreme, relative to the permutation distribution. This is the way in which we are going to do inference. There are other ways to do inference in the synthetic control methods, but again, I am looking today only at the original formulation. For example, Matias and Rocio, in fact, have done some very nice work on doing other modes of inference in synthetic controls. Okay, so let me try to explain with an example how this permutation inference work in practice. So here we have our test statistic, computed for West Germany and computed for all the countries in the North Pool. And we can see here is that West Germany is very extreme, in this distribution. And by the way, and if you look at the statistic, it's not just the treatment effect that we estimated. It's what we have here is the post period or post-intervention root mean square error divided by the pre-intervention root mean square error. Why is this? Well, when you look at all these units in the donor pool, some of them can be fit. You can fit them very well in the pre-intervention period, and some of them you can fit them not so well in the pre-intervention period. So that's why we are going to take this root mean square error, that is the difference between the the trajectory of the outcome for for the treated unit in the post-intervention period, and the trajectory of the synthetic control for that. The synthetic control that correspond to the treated units, we are going to divide it by the same difference in the pre-intervention period. Okay, that will be. I will explain this this idea, a little bit more later. Okay, some remarks about this type of permutation inference. The first one is that clearly, looking at the permutation distribution is much more informative than mechanically looking at p-values, because you can see, how far away the test statistic is relative to the a permutation distribution. P-values only gives you the ranking. The second remark is that depending on the number of units that you have in the donor pool, conventional significant levels may be unrealistic or maybe impossible, right? If you have like 19 units in the donor pool plus one treated unit, then you can hope for, having a like a p-value equal to 0.05. Otherwise, if you have less, you have fewer, you won't be able to attain, like 0.05 p-value, which, is something that some people really insist in doing. And something else that, it is going to be, I hope, clear in a second example is that the one-sided inference is often more relevant and is often, like more powerful. We will see that in this second example. This is an example about applying synthetic controls to study the effects of a tobacco control program that was approved in California in 1988. And what we can see here is like at the series of per capita cigarette sales in California, and before and after the passage of this regulation, the passage of this law that was is referred to as Proposition 99, and we have also the same series for the rest of the US. And again, this is a setting in which you wouldn't want to do like difference in difference, right? The trajectory of the outcome variable is completely different for California and the rest of the US. If I do difference in difference between this point and this point in time, I'm going to get something, but like there is no intervention there. Okay. However, like as for the German reunification example, there is a combination. There is a weighted average of other states in the United States that is able to reproduce the trajectory of tobacco consumption in California before the passage of Proposition 99, and also other. I won't talk about this, but also other predictors of tobacco consumption. And as before, we want to say, that this, what we observe there is the effect of the intervention. Okay, so what we are going to do in order to understand the inferential procedure a little bit better is like we are going to plot all these differences. We are going to plot all these differences in time between, California and the synthetic version in California. And if you do that, you obtain this graph, right? Like we have fitted California very well, in the pre-intervention period. There is a gap in the post-intervention period. Okay, so what is the permutation, like inference based on? It is based on the idea that now we are going to go to our data and artificially we are going to reassign, the treatment to the other units in the donor pool and see what happens. Okay, so here we are. These are all the synthetic controls for all the units in the donor pool. And something that you see here very clearly is that, and not very surprisingly, is that there are some units that they are so extreme that are the extreme of the distribution of the outcome that you cannot fit very well. Okay, like tobacco consumption in Kentucky is too high, and tobacco consumption in Utah is too low to be so that we can reproduce it using a weighted average of other, tobacco consumption in other regions. So while although the estimate for California is really extreme, in this permutation distribution, the comparison is not even fair, right? Because it's like we are, including here like units that we cannot fit very well, like before the intervention. Okay, if we take those away, let's do this. Now we have like only units that we can fit quite well, like units that the mean square prediction error, the difference between the outcome variable for California and for the synthetic control, like it's not more than twice, the units with mean square error, that is not twice the mean square error for California. So the mean square error here is the difference between the outcome variable for California and the outcome variable for the treated unit and the outcome variable for the synthetic control. So we are only keeping those that we fit almost as well as California. Again, you can see that this, California is extreme in this distribution, and this two-sided, one-sided inference is useful in the sense that, if there is like a negative fit for California, California may be in a in the synthetic control for, a placebo intervention, creating positive effects and, adding to, our statistical power. If you don't like this business of, taking away units that you cannot fit very well before the intervention, you can do as before, like looking at some relation between the post-intervention fit and the pre-intervention fit, and you can see for this sample, California is like a very, very extreme in this distribution. Okay. So let me talk about a couple of remarks about this permutation method. The first one is that it is the availability of a well-defined procedure to select the comparison unit what makes this the calculation of all these placebo interventions feasible. If we are going to choose a comparison based on some subjective measure of affinity between the units, it will be very difficult to reproduce that when you have to do it for like in many placebo interventions. The second point that is important to notice is that the permutation method that we describe now, it does not attempt to approximate the sampling distribution of the test statistics. And in fact, like sampling inference is going to be quite complicated in a synthetic control setting. Many times because we have the absence of a like well-defined sampling mechanisms, and often because the sample is the same as the population. So it is very difficult to think about what sampling inference means in this setting, at least like again in this original formulation of the synthetic control model. Okay. Many of you probably realize that this type of inference is going to reduce to classical randomization inference if the intervention is actively randomized. But again, remember that we are talking about a setting which you have like a aggregate units like regions or countries, and like a randomization in this setting is quite improbable. It's something that it doesn't happen in general. But more generally, we can think about this mode of inference as evaluating significance relative to a benchmark distribution for the assignment mechanism, one that we can implement directly in the data. And in what I have shown before, this benchmark distribution is uniform, but it doesn't need to be uniform. Like you can use you can use departures from uniformity, and Sergio Firpo and Possebon have a paper about this in the journal of causal inference. Many times people ask me why don't you use something like a propensity score method? And that is kind of a complicated, because it is in these settings with aggregate units, it is often difficult to articulate the nature of the assignment mechanism or even the specific nature of the placebo intervention, right? I was discussing yesterday in another meeting about think about what would be a placebo intervention in the German reunification example, France is going to get reunified with whom exactly, right? This inference is relative to a benchmark distribution, but it's not based on active randomization in the field. Okay, so now I will try to think about and discuss what are the advantages of these synthetic control methods, why we may want to use them. And in order to illustrate the advantages, I'm going to compare synthetic controls to regression analysis. That is a very familiar estimation framework. And in fact, years ago when we started talking about synthetic controls and we will go places, to present this work, people will ask, why don't you just run a regression and instead of doing this thing of a combination of weights at sum to one, can you do this using regression? In fact, you can do this using regression, right? And we have it here. You can take all the outcomes of the units in the donor pool in the post-intervention periods. These units are not treated in the post-intervention period, and we are going to regress them on the characteristics of these units. And I put a bar because I have augmented these metrics of characteristics with a row of 1, because I want I'm going to have an intercept in my regression as usual. But once I have that, I know how to estimate regression coefficients with the usual formula. Okay, and each column of this beta hat is going to be like the the regression coefficients for one of the post-intervention periods. Okay, and now how am I going to use this to calculate a regression-based estimate of the counterfactual of interest? That is, what would have happened with the treated unit in the post-treatment period without the intervention. So that's going to be, like a, my usual like a regression estimate that is going to be beta hat multiplied by, the characteristics of the treated unit. Okay, so now something that is easy to see, given the formulas that we have so far, is that this regression-based counterfactual in fact looks very, very much like a synthetic control. It's also like a combination of the outcomes of the untreated units in the post-intervention period. Okay, and you could calculate the weights. These weights, we usually don't do it when we run a regression this way, but you could calculate these weights explicitly. And given the formula that we have for these weights, you can also prove that these weights sum to 1. Exactly like for the synthetic control. So what is the difference between, like doing this with regression and doing this with the synthetic controls? Well, the difference is that these weights here, they may be outside of the 0-1 interval. And we know that we should allow that because, regression extrapolates. It's going to extrapolate to fit the values of the characteristics of the treated unit. Okay, it cannot be only based on interpolation. Okay, and also, as we will see in a moment, these weights are not going to be sparse. Okay, so a nice exercise, something that we can do is to calculate these weights for one of the like examples that we consider so far, and these are the weights for the example of the German reunification. These are the regression weights. Remember, the synthetic control weights were sparse. They were all of them, they were positive, and non-negative, and most of them were 0. Here you have like a non-sparse weights, and you have like some of them that are negative. And this is like a little bit more difficult to interpret, or much more difficult to interpret, the nature of this estimated counterfactual, because now perhaps, the contribution of Austria perhaps is moderated by, the negative weight of Italy or Greece. Okay, and it's very difficult to figure out what's going on here, and that's the cost that you pay for not having sparsity. So what are these advantages of synthetic controls? The first one is like a no extrapolation, like synthetic controls preclude extrapolation by using weights that are in this interval in between 0 and 1. The second one is transparency of the fit, like linear regression is going to extrapolate, so you can show that it's going to fit the characteristics of the treated unit perfectly, even if the untreated units are completely dissimilar in their characteristics, and they are very far away from the treated unit. In contrast, synthetic controls are going to make transparent the actual discrepancy between the treated units and the convex hull of the units in the donor pool. Also, unlike in regression analysis, we don't need data on post-treatment outcomes in the design phase of the study when we are trying to calculate this vector W star. To calculate W star, we don't need any data on outcomes after the intervention. Therefore, all design decisions, like we can make all of them without knowing how they are going to affect the conclusions of our study. Not only that, like these synthetic control weights can be calculated and pre-registered before even post-intervention outcomes are realized or before the actual intervention takes place. Okay, and this provides a safeguard against specification searches and p-hacking, something that is worrying many people now. Okay, the last two points are related. The first one is transparency of the counterfactual. Synthetic controls make explicit the contribution of each comparison unit to the counterfactual of interest. It's a weighted average is easy to interpret, especially when it is sparse, because the synthetic control coefficients are proper weights and they are sparse. They allow you to have a precise interpretation of the nature of the estimate of the counterfactual of interest and of potential biases. For example, if you think, no, I think that Austria in fact was affected by the German reunification, you can immediately see how this is going to bias your estimates. Okay, so we have mentioned a couple of times that synthetic controls are sparse, and here we have the explanation. Like a geometric interpretation of this sparsity. You can think about a synthetic control. What is this? A synthetic control is a projection of x1, on the convex hull of the characteristics of the units in the North Pole, and like that we obtain the synthetic control. So if x1 does not belong to a convex hull, and this is typically the case because of the course of dimensionality, then the synthetic control is going to be unique and sparse. If x1 belongs to the convex hull, the synthetic control may not be unique, and you will have candidates. Typically, you will have candidates for a synthetic control that may not be sparse. Okay, typically you will have an infinite number of solutions, although we know that there are sparse solutions among them. Okay, and the question is how we can decide among all these many solutions, and can we get a one that is optimal in some way, and is this optimal solution going to be as sparse as before? And this is related to one of the new techniques in the synthetic control literature. It's called penalized synthetic control estimators, and penalized synthetic control estimators are going to be very much like the usual synthetic control estimators, but they are going to add this term to the objective function. And this term is penalizing the discrepancy between the characteristics of the treated unit and the characteristics of each of the unit that contributes to the synthetic controls. So when this lambda is positive, it's going to control the trade-off between fitting well the treated and minimizing pairwise matching discrepancies between the treated units and the units in the synthetic controls. If you take this estimator, you calculate this estimator and make it lambda, going to 0, and the resulting estimator, in fact, can be calculated, without an approximation. There are mathematical techniques to do that. This is what we call the synthetic control, and this is going to minimize the pairwise matching discrepancies among all solutions for the unpenalized estimator. And not very surprisingly, when if you make lambda go to infinity, then only the pairwise matching discrepancies matter, and then you will get the nearest neighborhood matching estimator. That will be the solution. And so what are the advantages of the penalized synthetic control estimator? For lambda bigger than 0, the solution is going to be unique, and you will see that it's going to be sparse, and we will see in an example that is going to be sparse, although this is like a general mathematical result that I'm not going to discuss. And the presence of the penalization term is also going to reduce interpolation biases that occurs when you average units that are very far away from each other, and you can show that has the same computational complexity as the unpenalized estimator. So it's not more complicated to estimate. To understand how the penalized synthetic controls works in practice, instead of giving you the formal result, I would like to think about a very, very simple example. This is as simple as it can get. I mean, we have a one treated unit, 3 untreated unit. Unit 1 is a treated unit. We have 3 untreated unit, and X is one dimensional. We only have one dimension. Okay, and so you can see here that the unpenalized synthetic control estimator has 2 sparse solutions. The first one is the one that you obtain when you use x2 and x3 to interpolate x1, and in the second one you obtain when you use x2 and x4 to interpolate x1. Okay, but you immediately see that the first solution dominates the second solution in terms of the matching discrepancy. Okay, and it also is going to dominate an infinite number of non-sparse solutions that you obtain from convex combinations of the sparse solutions. Okay, but if you look at the original synthetic control estimators, all this infinite number of solutions look the same. I mean, in terms of the objective function, we need a way to discriminate among them. Okay. However, when you look at the penalized synthetic control estimator, as long as lambda is bigger than 0, the penalized synthetic control estimator is going to have a unique solution, and it's going to be sparse. In fact, you can see that it never uses the bad match x4. Okay, it never uses the bad match. As lambda goes to 0, it converges to W1 start. As lambda goes to infinity, it converges to giving all the way to x2. That is the nearest neighborhood estimator. That's the way this works in practice. Okay, so this was a like a little bit of a short summary of one new development, like in the literature of synthetic controls, and I want to talk about a second one, and this second one is like using synthetic controls for experimental designs. And what is this about? Let me try to explain this with a sample. Suppose that you are in a ride-sharing company, like something like Uber, and you are thinking about, a different compensation plan for workers, for drivers. Okay, and you think, okay, so like we have the usual compensation scheme and a new one, perhaps with higher incentives to drivers. And which one we are going to use? You are in the business analytic unit of this company. So something that you could do say is like, okay, so I will go to a city, and I will assign some workers, and like to the new compensation plans, and some workers to the old compensation plan, and see what happens. But as we described in the first slide, this is going to be problematic, because you have like workers in the same cities, like getting different amount of money for the same work, and that would be considered unfair, and it is unfair. Also, like the problem is that like if Rocio is like in the high compensation plan and I'm in the low compensation plan, probably Rocio is going to work longer hours because has higher incentives, as she may be still in business from me. So there will be all these type of interference issues that we make care about when doing an experiment. So what we may decide is like, no, what we have to do is to deploy or treatment at the level of the entire market. Okay, and perhaps we don't want to do it like treatment for 50% of the markets in the United States and no treatment for 50% of the markets in the United States. That could be super costly, perhaps, and also like it will be a little bit of a nightmare if if you decide to roll out, or if you decide not to implement the better compensation plan at the end of the experiment, right? So you may decide, okay, so I'm going to apply a pilot program in one market or in one city or in a few markets and cities, and I'm going to try to see what happens there. Okay, so in this case, you don't want to randomize. Okay, and you don't want to randomize because if you are going to apply this program to one city, like the city that you can get may be one that is not maybe not representative of the entire market of the United States, or maybe one that you cannot reproduce very well, that is especially idiosyncratic. And randomization will give you like unbiased nets ex ante, but I suppose you may be like in big trouble. So you want to do your experiment, you want to do your intervention, but in a non-randomized way. Okay, and the question that you are going to ask yourself is, which market or market should I treat, and which market or market should I use as a comparison or as a control? Okay. So what we have proposed in this setting is using synthetic controls. First, you find a set of weights that make a synthetic unit that reproduces the characteristics of the population of interest. For example, like all the cities where I have where my company is operating in the United States. And then you're going to create a synthetic controls for the synthetic treated unit. Okay. And in contrast with the observational case, here we are going to have two units, one synthetic treated unit and one synthetic control units. Okay, and these two objectives you can operationalize, put them in a nice objective function that you need to maximize, and this is what is going to give you optimal designs in synthetic control settings when you are doing experimentation, not randomized experimentation with aggregate units. And we have some work on this, and also Nick Dowchenko and others have been working these kind of techniques. And I have to say something about this, is that this is kind of new to academia, but it is not new to industry. Many companies are applying this type of synthetic control designs for experimentation, exactly because of the type of issues that we were talking about in the previous slide and this slide. And what we are trying to do here in this work is to try to formalize, many of the things that are already being applied, like in industry. In academia, sometimes we have like less capacity of randomizing across big aggregate units, okay? But sometimes happens, like sometimes we do that in like with villages and so on. Okay, so I have some time, but it seems that I went fast enough, so I'm ready to give closing remarks. And what I've been trying to say is that synthetic controls, like is they have gained popularity, but the reason that why they have gained popularity, in my view, is because they have many practical advantages of design for the estimation of treatment effects, especially in settings where you have like a few aggregate units. Some of them are, exposed to intervention of interest, and some of them are not. Okay, I didn't have the time to talk carefully about what are the requirements that we need for synthetic controls to work in practice. We saw some of that when we talk about the bias-bound formula, but as I said before, like as for any other statistical procedure, and especially those that want to estimate causal effect, the credibility of the result that you're going to obtain depends very much on how diligent you are, like applying these methods, and the type of data that you have, and contextual characteristics of your problem that have to be met. And like I have a paper, a recent paper in the Journal of Economic Literature that covers cover all these aspects in quite a lot of detail. So what are some open areas of research for synthetic controls? Like, well, this is quite a new method. So there is a lot that has not been done. And some people have been working on sampling-based inference, although, like in my opinion, there still is quite a big open field in terms of potential improvement. Not much has been done in terms of external validity, sensitivity to model restrictions. There is some work with estimation with multiple interventions, but also very interesting set of issues. And also much more work needs to be done on data-driven selectors of VH. You remember these were the weights that we put to the variables, to the predictors that we're using for estimator, and other things like mediation analysis. There is very little work done for synthetic controls, and it's something that my guess is that is going to happen in the next few years. And also another area that is a favorite of mine, as you could see before, that is of a high interest, is the use of synthetic controls as experimental designs. And there are many contexts, especially in industry, but also in academia, where we need to carry out experiments at an aggregate level, and we lack a lot of tools for doing that. Like most of the tools we have today is for the case in which we have many micro units that are treated and many micro units that are not treated, and this is not exactly the case. And this is interesting because it make also this a case in which the availability of methods may restrict what you do in practice. I mean, sometimes people tend to do what we know how to do, and this is a a new set of potential experimental designs that could be used quite a lot in practice. Also on computation, this is important. We need many more results on robust and efficient computation of synthetic controls, and the good news about this methodology is that on the empirical side, many of the events and pulse interventions that we care about do take place at an aggregate level and affect the entire aggregate unit. So there is a lot of many possibilities, many potential empirical settings where we can apply these methods. So let me finish looking a little bit at some resources that I have used in this presentation and some extra resources that that you can use for synthetic controls. Most of my material in this presentation comes from my own work, and this is you have the reference here, and in particular, like it comes very directly from a recent paper in the Journal of Economic Literature on feasibility, data requirements, and methodological aspect of synthetic controls. There is also like some information here about like a code for calculating synthetic control estimators, calculating the unpenalized synthetic control estimator, also calculated the penalized synthetic control estimators. And as I said before, like many people have contributed to the literature on synthetic controls, and I wanted to provide some references here, so like you can access this material. And I hope that these slides are going to be available after the presentation. Okay, and that's all I have. Thank you very much.
I'm Rocio Titiunik from Princeton University. Matias and I are going to jointly talk to you about regression discontinuity designs. I'm going to be doing the first part, and Matias is going to take over the second part, and we're going to have 10 minutes in between. We are going to continue the causal inference on program evaluation framework. And so we're going to be thinking about a framework where our goal is to learn about treatment effect. So basically the effect of a treatment or a policy or an intervention. And as we know, if the treatment is randomly assigned, then it's going to be relatively easy to estimate effects, although there can be complications, but at least straightforward how to proceed. But if the treatment is not randomly assigned, then we're in the world of observational studies, and we need to invoke some sort of assumption like selection of observables, instrumental variables assumptions, some other assumption. The feature that all these assumptions will have in common is that they're not going to be known to be true. They're not going to be true by construction. They're going to be held as assumptions, and we're going to hope that they're true, and we're going to do more than that. We're going to try to provide some evidence that is consistent with their being true. But it's always a complicated problem, and how credible are our estimates and our conclusions based on observational studies. So the regression discontinuity design is one observational study, one type of observational study that shares some of the limitations that are inherent to observational studies, but has some advantages relative to other observational studies. And the first one is that it's based on a simple assignment rule, and this rule is based on external factors. And this creates an objective basis to evaluate the assumptions that we're making. And this objective kind of grounding in reality and in some like actual rules that are verifiable allow us to falsify the design in a way that other designs can't be falsified. And so this increases the credibility of our designs. They're also easy to interpret, and of course they have some peculiar characteristics and some limitations. And one in particular is that the parameter that we can study is very local, and we're going to see what that means. So what is a regression discontinuity design is defined by a triplet of a score, a treatment, and a cutoff. So the units in the study receive a score, and I'm going to call that score X. And the treatment is going to be assigned based on the score according to a rule. And without loss of generality, we're going to assume that the treatment is given to units whose score is greater than the cutoff, and the treatment is withheld from units whose scores are below the cutoff. And when I withhold the treatment, I'm going to call that control. And so, if you plot the score on the x-axis and you plot the, probability, the conditional probability of being assigned to the treatment or the control as a function of the score, you're going to see that it's 0 for all values of the score that are below the cutoff, and it's 1 for all the values that are above. And so there's a discontinuous jump in the probability of being assigned to treatment from 0 to 1 in all RD designs. And so there's, abruptly, I go from having a probability 0 of being assigned to the treatment to a probability of 1. And so the regression discontinuity design is basically a design that is based on this type of discontinuous assignment to treatment. And what we're going to do is we're going to place assumptions on top of this assignment rule so that the abrupt change in this probability of treatment assignment will use that abrupt change as the basis to learn about the treatment effect. So there's many aspects of the regression discontinuity design that we can talk about. We call it the regression discontinuity taxonomy. There are different frameworks, and what we call the frameworks or approaches are approaches for identification and interpretation analysis. So we can make continuity assumptions and extrapolate, or we can do local randomization assumptions. We're going to talk about this in detail. We can think about settings where the score is continuous versus where it has repeated values. There's also different kinds of settings in terms of whether compliance with the treatment is perfect or imperfect, and that distinguishes between sharp and fuzzy. There's also situations where we can have a multidimensional cutoff variable, a multidimensional score variable. We can also think about time as a running variable or dynamic treatments. And so those are going to define different settings that I'll discuss briefly and give you an overview here. We can also think about different parameters of interest. So we are going to base most of our discussion in average treatment effects of some sort, and we'll discuss, different types of average effects. But like in any other, causal inference setting, we can think about quantile effects or distributional effects, and we can think about partial effects. We can also think about, heterogeneity by subgroups and subpopulations, and we can also kind of think about generalizing the parameter of interest and talking about extrapolation, which if we will have time, we'll discuss later. So what I will do is I will give a little bit of an overview about, the general frameworks, and I'll talk a little bit about different kinds of settings to give you a flavor of what different kinds of regression discontinuity setups you can encounter. The regression discontinuity is not something that you design typically, it's something that you come across. And so to give you an overview of the different types of designs that you might come across might give you an idea of, when can I apply these tools with different kinds of contexts. And then in the final part of my presentation, I'll talk about local randomization methods, and Matias will take it from there. So let me introduce a little bit of notation, and I'm going to introduce a notation in the context of a randomized control trial, or RCT, because we're going to be discussing the differences between RCTs and regression discontinuities in the next hour or two. So similar to Alberto, the notation is going to slightly change. So Alberto had yn, I am going to have y0, but we're going to adopt the potential outcome framework. So we have potential outcome under control, y0, we have the potential outcome under treatment, and we have x. In an RCT, you can think of x as being any covariate. In the RD design, that's going to be that, the score. I'm going to index units from by I from 1 through n, and the treatment is going to be t, and it's going to be a binary treatment for the rest of our presentation. And in an RCT, as we know, by virtue of the treatment being randomly assigned, the treatment is going to be independent of the potential outcomes, also of any pretreatment covariates. And the observed, that we're going to have an observed outcome. So the data that we observe is going to be the observed outcome. We're going to call it y, and then data on t and x for all the units. And of course, we have the fundamental problem of causal inference that we only observe potential outcome under control if I give you the control, and we only observe potential outcome under treatment if I give you the treatment. And that is a fundamental problem, but in the case of an RCT, it has an easy solution, which is just go to the treatment group and get the observed outcome in the treatment group, compare that to the observed outcome in the control group. At least if we're talking about average treatment effect, it has an easy solution. We can just readily identify the average treatment effect in the way that I know everybody connected today knows. So that's the setup of an RCT. I'm going to keep the notation, and now I'm going to change the assignment. I'm going to go from an RCT to a regression discontinuity. And so what's going to happen is if you have the independence of between t and the potential outcome is really going to be replaced by something that is has nothing to do with independence, which is basically an indicator that it's going to be 1 whenever our score is above a known cutoff. That's going to be fixed, and 0 otherwise. The data is the same data as we had before. I'm now using x is going to be the RD score. And we still have the fundamental problem of causal inference, but we don't have the easy solution anymore because we don't have independence between the treatment and the potential outcomes. And so now the question is, what are we going to do to try to identify, some kind of average treatment effects, and what can we do? And so we're going to talk about two different, so the first thing to note is that there's no identifying assumption that holds by construction. So this continuous rule for the assignment of the treatment doesn't imply, in any way the identification assumptions that we need. And so we need to place those assumptions on top of the assignment rule. And so it's up, we have different choices of what assumptions we want to impose. And then based on those assumptions, we'll be able to, identify a treatment and go from there and think about estimation and so on. So we're going to talk about two kinds of assumptions. And those are going to be focusing on different types of effects. So we're going to define, in what we call the continuity-based assumption, we're going to assume continuity of regression functions, and we're going to define the parameter of interest as the average treatment effect at the cutoff. So this is an average treatment effect at the cutoff. It's a little bit different from what you are used to seeing, because we're not used to seeing average treatment effects at a particular point. And so Matias will talk about the implications of that for estimation and inference. When we can also make different kinds of assumptions, and instead of making continuity assumptions and focusing on the average treatment effect at a point, we could define a parameter of interest that is the average treatment effect in some window or some interval around the cutoff. So it's not a point, but now an interval, and we can think about the average treatment effect in that interval, and that's what we're going to call the local randomization based approach to the analysis. Both of these analyses, each one of these approaches is going to make a different assumption that is going to be placed on top of this continuous assignment rule. It's going to have a different way of exploiting the idea that above and below the cutoff we're going to make some comparison, and we're going to discuss both of them in the next hour and 50 minutes, hour and 40 minutes. I'm going to be focusing on local randomization. Matias is going to come back and then he's going to talk about continuity based. So when you think about continuity based, this is the canonical plot that you're going to see to represent this approach. So you're going to have the score in the x-axis, and then you're going to have the potential outcomes on the y-axis, and you're going to plot in particular what we call the regression function, so the conditional expectation of the potential outcomes as a function of the score. And so basically you're going to have the regression function under treatment, the regression function under control, and you're going to define the treatment of interest as that vertical distance between these two regression functions at the cutoff. And you're going to base, of course, this is an unobservable effect, and you're going to base identification on continuity assumptions about these functions. And Matias will give you more details about this. So in the local randomization approach, we do something a little bit different, and I'll come back to talk about this by the end of the presentation. We basically assume that there's some window. So basically we define the average treatment effect in this entire region here, in this entire window, and we assume that in that window, basically the regression functions are not going to be functions of the score, and that's going to allow us to estimate and recover treatment effects. So those are two different approaches. We're going to cover those in the remainder. I'm going to cover local randomization. Matias will cover continuity-based. But before I go into the details of the local randomization approach, we wanted to give you an idea of this taxonomy that I was talking about. What are the different aspects of regression discontinuity that you might encounter along these different dimensions? And so we'll give you some of them here, and then we'll talk about resources that we'll share with you. We have created a GitHub site where you can download the materials for today, and we'll also share references and resources. So one distinction that is very important when you encounter regression discontinuity design is whether you have perfect compliance with the treatment or imperfect compliance with the treatment. So here on the left, I have what we call a sharp RD design. The literature calls sharp RD designs. Where this is basically a design where there's perfect compliance. So everybody with scores above the cutoff is assigned to the treatment. That's always the case, but also receives the treatment. So now we are looking here at the conditional probability of receiving the treatment, not being assigned to the treatment, but the conditional probability of receiving the treatment as a function of the score. And when you have perfect compliance in a sharp RD design, the probability of receiving the treatment above the cutoff is 1, and the probability of receiving it below the cutoff is 0. And so there's a full jump from 0 to 1 in the probability of receiving treatment. When we have non-compliance, that jump still exists. So it's still the case that when you cross the cutoff, the probability of receiving treatment changes discontinuously, but that is not necessarily a change between 0 and 1. So in this particular plot here, you're seeing a one-sided compliance. So everybody whose score is below the cutoff is in the control condition, doesn't receive the treatment, but above the cutoff, there's a fraction of the treated people, the treated units that don't take the treatment. And that's why you see the jump in the probability be smaller than 1. So it jumps from 0 to something that's smaller than 1. So this is typically what you'll see in a fuzzy RD design, which is a jump in the discontinuous jump in the probability of receiving treatment, but it's smaller than 1. And we can still use the ideas of the regression discontinuity. Typically, if you are using a continuity-based approach, you're going to define a parameter that's going to, it's going to be a little different from the sharp parameter, and it's going to take this ratio form that is going to be, sort of it's going to have an analogy with instrumental, like two-stage least squares or instrumental variables type of estimates that you might be familiar with, where you'll have an intention to treat effect divided by a first stage effect. And that's going to be a canonical estimate that we can define in both frameworks. So you're, again, like it happens in say the instrumental variable framework, you're going to have to bring some additional assumptions to say exclusion restrictions or local independence assumptions to interpret. But this is one distinction that we might encounter in practice, and fuzzy RD designs are very, very common. The other kind of regression-related design that you might encounter, and this is common in economics in particular, is what are called kink designs. So these are situations where you have a treatment or a policy, but the policy is not binary. It's a continuous policy that depends on a score via a formula, and the formula introduces kinks. So it could be, for example, a piecewise linear rule that at particular levels of income changes the rate at which you have to pay taxes, or particular levels of income changes what kind of unemployment insurance you can get. And so this rule introduces kinks. And so when you look at outcomes, so you might expect that the outcome, so the rate at which the policy is operating is changing at this kink point. And when you look at outcomes, you're not going to expect a jump in the outcome like in the typical RD, but you might expect a kink, like a change in the slope right at the cutoff, which basically is equivalent to a jump in the first derivatives of the regression functions. And so you can define parameters of interest that are kind of analogous. You can define them analogously and identify them with similar assumptions to the usual parameters, but you're going to have, instead of the levels of the regression functions, you're going to have the first derivatives. And when you think about kink designs, they can be sharp with perfect compliance, or they can be fuzzy with imperfect compliance. And you can also think about them in terms of continuity based or local randomization based. So a lot of these taxonomy dimensions are cross-cutting. So you can have local randomization fuzzy or local randomization sharp. You can have a lot of intersections between these different categories. All right. So another design that is type of RD design that is very common and that you might encounter in practice is an RD design where we have either a score or a cutoff that is not one-dimensional but is multi-dimensional. So here on the left, I have what we call the multi-cutoff RD design. So we might have a regression discontinuity rule that uses some cutoff for some population, and then for some other population uses some other cutoff. And so really what you have is regression functions for one population and regression functions for another population. And you have, if you go cutoff by cutoff, you have, two different two different treatment effects, right? So imagine that I have two cutoffs here, then I have the usual RD parameter, but now I have, one RD effect for cutoff 1, another RD effect for cutoff 2. So this makes it also opens the door to, you can, first of all, very easily look at heterogeneity of treatment effects across cutoffs, but then it opens the door to think about what, what would have happened, what would have been the effect, let's say this population is exposed to this cutoff and this is the effect, what would have been the effect for the same population at the higher cutoff? And so this introduces some ideas about extrapolation, because as we'll talk about later, and Matias will also emphasize when he talks about continuity-based, a lot of these methods will be, a lot of these regression discontinuity designs will be focused on very, very local effects. And so the idea of, what's going to happen, what happens to this effect as I go away from the cutoff is going to be an important question that, we're constantly looking for ways to try to answer that question. Once we have answered what's the effect at the cutoff or what's the effect in this very small window around the cutoff, we do want to know, what's the effect beyond that. And for that, we're going to need to make, external other assumptions, and multiple cutoffs is one way in which we can get at that. Another way in which we can have a multidimensional RD is when we have a score that is multidimensional. So for example, when I have a language exam and a mathematics exam, and then I'm gonna place children in a particular program when they score above a cutoff in each score. And so basically what that creates is it's an entire boundary instead of an entire boundary of points, an entire boundary where the treatment is changing from when the status is changing from control to treated. And again, so basically we're going to have an infinite number of parameters that we could estimate along this boundary, but in practice what's typically going to happen is that you're going to choose several points along that boundary and you're going to try to estimate the effect there. And again, you can basically define and generalize the parameters and the approaches for these different types of multidimensionality. One important particular case of a multidimensional, two score RD design is a geographic one in particular. That is, it is commonly used in a lot of areas of, social science and economics in particular, where you can think of the score, units in space, and each unit having a latitude and longitude score. So, two scores that determines the location, and then having a boundary that separates a treated area from a control area. So a treatment that changes this continuously at the boundary. And then you can think about estimating different treatment effects along the boundary. And so basically you can think that if you stop, and you focus on that particular point of the boundary, then at this point in the boundary, you can calculate the distance of all of these units to this point, say the geographic distance of all of these points, all of these units to that point, and then you can estimate a unidimensional RD effect at that particular point. You can repeat that for as many points as you want. And so basically it comes down to all kinds of, there are different kinds of RD designs, but they all share, they all share kind of the same basic structure. First of all, they all share the fact that obviously there's a discontinuous change in the probability of receiving treatment at a particular cutoff. This cutoff might be one, might be, by more than one, might be multidimensional. The score might be single dimensional, multidimensional, but there's always going to be this formula that creates this jump in the probability of receiving treatment, or at least, a kink in a more general rule. The causal effect that we're going to be able to, identify with this design is going to be different in general from an RCT, and I'm going to discuss that more. All of these RD designs, regardless, are going to be based on this idea of exploiting this variation, this like abrupt change near the cutoff. And we're going to be introducing some assumptions that are going to basically give us some sense of comparability, that if I go to units just above the cutoff and I go to units just below the cutoff, in some sense, those units will be comparable, or we're going to be able to use them to approximate and get at something that might be comparable. There is no overlap, right? So meaning that every unit that is treated, if you think about a sharp, right, think about perfect compliance, every unit that is treated has a value of the score that is higher by definition than every unit that is controlled. And this is it's a lack of, there's a lack of overlap in this very important covariate. Typically RD designs are given based on covariates that are very important, and I'll give you an example very soon. And so this lack of common support, it's going to basically imply that treated units and controlled units are going to be different by construction. And so we're going to need, something to, basically we're going to localize and go close to the cutoff to try to, regain comparability of some sort. We're going to talk a little bit more about how, how to analyze them graphically, and this is going to convey a lot of information about the design. And then another takeaway will be falsification and validation methods that Matias will discuss later. So let me talk a little bit about how to visualize the design. And for this, I'm going to use software. So here is the information of where to get our where to access our software packages. So we have we'll have packages for RD estimation, visualization, and inference in Python's data on R. And you can have the GitHub page over there. You can get the multiple, you can download them and install them in your preferred platform. And I'm going to use them to, I'm going to use now a little bit of those packages to illustrate how to use them to analyze a real design. So the application that we are going to analyze, and Matias will also analyze later, so I'll just introduce it once and then we'll come back to it at various points. It's an application published in the QJE in 2007 by Ludwig and Miller. The question is to study the impact of giving municipalities assistance for the rollout of Head Start, and to look at that assistance on infant mortality in municipalities. So the unit of analysis is municipalities in the US. The treatment is whether the municipality received assistance to roll out Head Start. And the score is a poverty index. So important, the poverty index that they use is poverty index before. So this is happening in the 70s. So they use the poverty index of according to the census of 1960 to rank municipalities according to most poor to least poor. And so this is important, right? Because it gives you an idea of why regression discontinuities are in a way the opposite, in one sense, the opposite of randomized controlled trials. Because in this case, we order municipalities from most poor to least poor, and then basically the way they did it is because of budget considerations, they could give assistance to 300 municipalities. So they counted, started with the poorest municipality until the 300th poorest municipality, and that's and where the poverty index of that number 300 was the cutoff, and so that determined the cutoff to be that particular number, which means that basically you sorted all the municipalities by poverty, and all the poorest municipalities are in the treatment group and the control group. So basically this lack of common support is a lack of common support in the poverty index that is going to be highly correlated with the outcome of interest, which is child mortality. So mortality of health, of causes that might be affected by Head Start in children 5 to 9 years of age. So you can see how this, immediately creates a problem of comparability between treated and controls. So I'm going to visualize this. I'm going to talk about how to visualize the design, and I'm going to show you an RD plot. I will just show you a very quick little bit of code. We have shared this data set and the code with you in our GitHub page. You'll find it in the NBER link, and you can download it, either run it now with me, or you can download it later and replicate it yourself. So I just have the outcome, and I have the score, and then we have several covariates that for now I'm not going to use. And I'm going to create a treatment indicator. So the only command that I'm going to focus on here is I'm going to use the command rdplot, which is going to plot the outcome as a function of the score, giving the particular value of the cutoff and with a few options that I'll talk about. This is actually the default, and in the default, you can actually remove even that. And that's going to be the default. And so this is what a regression discontinuity, or what rdplot looks like. We have, the outcome on the y-axis, the score on the x-axis. We have the cutoff, and we can see there's a jump at the cutoff. So the rdplot is built with two ingredients. One, the lines that you see here, those are global polynomials, so separately fitted to the right and to the left. In particular, the default is in this command rdplot, it's a fourth order polynomial fitted of y on x and on each side. You can see here that, and then you can the points here are so the lines are the fits from global polynomials, fourth order on either side. The points are local means. So basically, we split the support of the running variable into intervals, and for every small interval, we calculate the mean of the outcome. We plot that as a point. The fit is fitted on the raw data, not on the point, right? And so the idea is that the global fit will give you an idea of the overall shape of the regression functions, and the points will give you a better idea about the local variability around the functions. And what we are looking for is, well, if there was an effect of the treatment is changing, there is no head start assistance to the left, there's assistance here to the right. What we should see is, if there was a treatment effect on the outcome, we should see a big jump. Now, what we see here is, well, it's a huge jump, right, at the cutoff, but we need to be a little careful here because there seems to be quite a bit of overfitting going on. And so this is a problem that Matias will talk about later when we use, so remember that we are trying to estimate what happens right at the cutoff. And so we're trying to estimate a treatment effect at the cutoff point. We're trying to approximate that regression function at a boundary point. There's no data to the left to estimate this intercept here. There's no data to the right here to estimate that intercept. Boundary points have the feature that make global polynomials very unstable and lead to overfitting. And so if I run the same rdplot, but I use a linear polynomial instead of a global, you can see the difference. The local means are not moving, right? What your brain is doing is, all that is moving is the global fit. So what your brain is doing is, in the first plot, your brain says the effect is huge. In the second plot, your brain says the effect is moderate, and nothing has changed. All that has changed is how we fitted the global regressions. So this is why you cannot use really an rdplot to formally estimate and to formally analyze a regression discontinuity design, because there's there's many possibilities for how you can present this plot. Nonetheless, it's a useful tool to visualize where the data points are, how much variability you have in the treated and the control group, and it's also kind of, I'm setting up for Matias to come back and tell you why we're going to be focusing on polynomials of lower order when we use continuity-based analysis, and why we want to go local to the cutoff, and how we're going to have to take care of the problem of boundary bias and the fact that this is a boundary point. All right. So for now, let me go back to the slides. We have more information to give you about how to particularly choose the bins, for example, in an rdplot, and just invite all of you to consult the references about optimal selection of bins and the number of bins if you are interested. But in the interest of time, I'm going to keep moving. Oh, apologies, keep moving along. And I want to talk for the last minutes that I have in my presentation. I want to talk about estimation and inference in particular. So basically, up until now, I gave you a big overview of different kinds of issues, and then how to, how to visualize an RD design. And now I want to get a little bit more formal in terms of how to proceed to, for how to estimate and how to perform statistical inference under different assumptions. So as I've been hinting since the beginning, we're going to discuss two approaches. I will discuss local randomization. Matias will discuss continuity based. There are a lot of things that these approaches have in common. And so basically, we are going to need localization. So we're going to go close to the cutoff before we do anything else. And why? Because our assumptions are going to require, unless we want to make very, very strong parametric assumptions, we're going to need to go close. And so this will mean that we either need to select a window in the case of local randomization, or in the case of local continuity, we need to select a bandwidth. Then when we talk about point estimation, we're going to have a choice between what kind of methods we're going to use for point estimation, and for inference. We're going to have a focus on non-parametric methods. And in local randomization, we're going to have a choice between fine sample valid methods and large sample methods. So basically, we're going to focus on these two approaches. There are many others that exist, empirical likelihood methods, derivation methods, etc. Those are not as widely used in the social sciences, and sometimes require kind of ad hoc choice of tuning parameters, which is something that we will try to avoid. And we'll talk about how to do data-driven and optimal choice as much as possible of any tuning parameters that are needed. And so we are not going to, in general, methods that require users to choose these tuning parameters by hand are going to lead to some, problems in terms of replicability and so on. So, but those exist, and Matias and I are writing a review article for the Annual Review of Economics, and there we will, we provide comprehensive sites in case you are interested. Okay, so I'll talk in the final part about the local randomization approach to RD design. What is the key assumption? So as I said, the regression discontinuity is defined by this discontinuous treatment assignment rule. That is the definition of it. But that's still not enough to be able to, say, well, there's an average treatment effect here that's identified. I need something more. So in the local randomization approach, we impose an additional assumption. And the assumption is basically, informally, it says, it's really the original assumption that that was kind of the intuition behind the first RD paper in 1965, which is the assumption that, okay, if I go to a window around the cutoff, a little positive number W, so I go C plus W, C minus W to a small window, then there exists, such a window exists, and in that window, subjects are as if randomly assigned to either side of the cutoff, and therefore to the treatment. And so that is the intuitive assumption. So the intuitive assumption is there exists a window near the cutoff where this behaves as a randomized control trial. How to formalize that is actually requires a little bit of work. And so we're going to split that assumption into two. So the first is going to be that the joint probability distribution of the scores for units inside the window is going to be known. And that's what would happen in a randomized control trial if you assign the value of the score randomly. You would know exactly the joint probability distribution of that score. So we're going to assume that it's known. In practice, you don't need yeah, you don't need to know it, but you might, things like assuming that everybody has 1/2 probability or whatever it is will imply that you know this joint distribution. So we're going to assume that we know it. And then we also need to assume that inside that window, the potential outcomes are not affected by the score. So basically it's an exclusion restriction where the potential outcomes inside the window don't depend on the value of the score. And so this is a stronger assumption than you're going to see later, that the standard assumption of continuity based. And if we make these two assumptions, okay, so then we can say, well, then we have a sort of randomized control experiment in this window. Why is this stronger than continuity? Because, given these assumptions, it's not only true that the regression functions are continuous at the cutoff, which is what you'll need for the standard continuity-based approach, but they're also inside the window, they're completely unaffected by the running variable. And that's what allows us to treat this as, an experiment. So if you think about the typical RD plot, so you have on, this is the RD plot that I introduced before. So this is the typical, regression functions as a function of the score. If this is poverty and this is child mortality, the potential outcomes are going to have, a relationship, there's going to be a slope. But if you think about what that similar plot would be in a randomized experiment, if you take the score to be, the random number that you use in your computer to assign people to treat and control, and then you plotted the regression functions, so the regression functions, the potential outcomes, as a function of that, pseudo random number, you would see basically no relationship whatsoever between the regression functions and that number, because that number is just an arbitrary thing it's an arbitrary device that is unrelated to the characteristics of the units. So the idea is, if we want to use the ideas of the, of the analysis of experiments to analyze an RD design, we need to kind of put this, this feature of a randomized experiment into, as an assumption into the RD design. And so the way we do it is by basically localizing, as I was saying before, is of course, overall, we're not going to be able to assume that there is no relationship between potential outcomes and the score, because by definition, as I said, the RD score, if it's poverty, if it's, and potential outcomes are, outcome is mortality, those two things are going to be very strongly correlated. But what we're going to assume is that there is a window, it could be very, very small, right? Close enough to the cutoff such that if I'm able to get close enough, the relationship between the potential outcomes and the scores disappears. And so these regression functions are flat, as they would be in an experiment. And in addition, I know, or I can assume plausibly what is the distribution of that joint distribution of the score in that window. So, for example, if I have, if I have 100 units in that window, and I have, 60 and 40 in treated and control, and I assume a fixed margins randomization took place, which, hypothetically, then I can use that treatment, that distribution for thinking about and analyzing this as an experiment. So basically, if you're willing to make those assumptions, and we'll see, and we can validate this to some extent, then you can analyze, if this assumption holds, then basically you can deploy all of the tools of the analysis of experiments that you already know to analyze a regression discontinuity design. But so there's two steps that we need for implementation. And the first one is we're going to need to select that window, right? We need to select that window. We can deploy all the analysis, all the tools from the analysis of experiments once we are in that window, but we need to know where that window is. And so the first step is to select it. And the second step is, well, given that window, we can use, just perform estimation and inference. So the window selection step can be a challenge, although we'll show you a data-driven method to do it in a minute. But it is but in general, this, the challenge of using this approach is that the assumption of, active randomness, those two components, is really, it's going to be strong, and it's going to be a good approximation only if you really are able to go very near the cutoff. And so that will, that will probably lead you to discard a lot of observations, and you're going to end up with small sample. And so that can introduce some challenges in terms of statistical power and so on. So how to choose a window? Well, you can do several things. You can use pre-treatment covariates, which is our preferred method. You could choose, you could find a neighborhood where the outcome and the score are independent, but doing some independence tests, or least preferred choice, you can just do it, just do it based on some substantive knowledge that you have in an ad hoc way. So the preferred way is to use some sort of data-driven method that allows you to validate and defend how you did it. So the idea of the covariate, so the idea of using pre-treatment covariates to choose the window is very simple. Is that if you have a covariate or more than one that is related, so here I'm plotting the regression function of the covariate as a function of the score, and this is again the cutoff, and this is the true window where local randomization holds. So imagine that you can find a covariate that is very related to the score overall, okay? But it's a pre-treatment covariate. Okay, so you know there's no treatment effect because this is a pre-treatment covariate. So you know there's no jump at the cutoff, and you also know the covariate to be very correlated with the score. And so what you're going to do is then say, well, if there is a W where the local randomization holds, if I start with the largest W, with the largest window, and I do say a difference in means test, so I test the null hypothesis that the average of the covariate, the mean of the covariate in the treatment group is different from the mean of the covariate in the control group in the largest possible window of the entire support, I'm going to reject that. I'm going to reject that null. And if I keep doing, if I do it for a slightly smaller window, again, I'm going to reject the null that the covariate distribution, the covariate means are the same. But there's going to be a point when I hit the window where local randomization works, when I'm going to stop rejecting that hypothesis, and then I'm going to stop rejecting it there, and then I'm going to fail to reject it in all the smaller windows contained in it, right? So this gives you a data-driven method of choosing the window by basically choosing the largest window where you fail to reject the null that the covariate distributions are the same in that window and in all windows that are contained in it. And I will show you in a moment how to implement that with the data. Once you found that window, then you can deploy, as I said, all the tools from the analysis of experiments. You have the 3 canonical choices per, Imbens and Rubin book. So you can do randomization, inference, Fisherian methods. So these methods are actually related to the methods Alberto was talking about, permutation methods to use in the synthetic control design, where you will permute, run, and regenerate different versions of the treatment, and then create, randomization distributions under the null that way. So these methods are going to be finite sample exact. The advantage of this method is that if you have to do it in a very small window, they're going to still have known properties in this very finite sample. You can also use Niemann methods where the potential outcomes are fixed, but you rely on large samples, or you can use the standard large sample methods based on random potential outcomes that are large sample methods. All of these methods will require a window selection and then a choice of the test statistic. If you're using Fisherian or Niemann inference, you're gonna need to think about the particular assignment mechanism as well. Let me go for the last bit back to the code, and I wanted to show you, if I can move this away. Yes. The RD plot that I just did a few minutes ago was part of the RD robust library or command. The command that I will use now, which is the RD win select, is part of the RD log run. So basically we have separated the RD software by RD log run and RD robust by continuity based methods and local randomization methods that are completely separate intentionally, kind of to emphasize the fact that they're based on very, very different assumptions and very different conceptual understanding of the design in some sense. So what I will do here is I have in X is the score. And I have a number of covariates that I'm going to pass to this window selector. I also have the cutoff, and I'm going to have a few parameters here. So I'm going to run it. I'm going to run it. And while it's running, I will continue talking. So basically what this is going to do is going to implement a window selector. It's going to start from the smallest possible window. And we're going to impose a minimum of 10 observations on either side. Of course, one of the challenges of the window selector is that you have to ensure that the last window that you test doesn't have very, very few observations, because of course, with one observation on either side, you're always going to fail to reject any hypothesis. You will have no statistical power. So, one recommendation based on some power calculations that we've done is to use, a minimum of 10 observations on either side. So you start with a minimum window in terms of, 10 observations on either side, and then, which is this one. Remember, the cutoff is about 51.1. And then you start increasing the window symmetrically on either side. You can increase it by a step of length, or you can increase it by number of observations, and you continue to perform balance tests. And then here we're doing balance tests for all the covariates and keeping the minimum p-value. And this is the covariate associated with a minimum p-value. And then basically what's going to happen is that, in cases where you can find a window where this works, you're going to find that the p-value starts being large. And as you make the window larger, the p-value is going to start to drop. And it's going to start to drop until it falls below, conventional levels of significance. So if I show you in the slides, I ran it for many windows, which takes a little bit of time, so I didn't want to do it live. And what you see here is that this is a typical plot for the window selector. You have for small windows, and here's the length of the window. This is the length of the window that I'm plotting, and here's the minimum p-value for each window. So for windows that are very small around the cutoff, so length 1 or 2, the minimum p-values are all very large, meaning that basically you cannot reject that the distribution of these covariates is the same. And then as you increase the size of the window, as you move to the right, the length of the window, those p-values start to decrease. They're not exactly monotonically. Sometimes they go up and down, but but there's a trend, right? That as you increase the length of the window, this covariate balance gets worse and worse, as you would expect, because the outcome and the score are very correlated, and this covariate is very correlated with the outcomes. And so basically, what you're going to do is, in this case, this is the last window, right? This length right here, right, which is about a little bit under 5 in terms of the the poverty rate, the poverty index. This is the last window where the p-value is about 0.15. The recommendation is to use a threshold for the p-value that is much higher than the conventional significance, because we are flipping the null here, right? We're interested in the lack of effect, not non-effect. So that kind of changes the way you think about testing. And so you want that p-value, that threshold to be higher. We recommend 0.15, but as high as possible. So this is the last window where basically in this window and all the windows smaller than this one, right? All the p-values are all higher. And so there's no window here or on any sub-window where you reject that null hypothesis. So basically that would say that this window is the chosen one. And so given that chosen window, which ends up being, it's around here. So you see how you drop below 0.15 in this window. So we choose this one as the window. Now you can go to that window and use, I'm going to use an RT plot to give you an idea of the effect. So if I go to that selected window and I plot it, what the local randomization approach does is, after I've localized and I got very, very close, then I just do a mean. I just calculate a constant polynomial, a mean on either side, and I can look at the effect and I can see an increase in mortality that you can replicate with the command rd randinf, which will basically give you the difference in means and give you the p-values from finite sample and large sample. All right, 10:54. Okay, so I have 1 minute. I'm gonna do this, and this is where Matias will take over when we come back from break. I'm not gonna offer conclusions or big lessons because Matias will be doing that at the end of his part. So I will kind of leave you hanging. We have a 10-minute break. So we are going to be back at 11:05 Eastern in exactly 10 minutes, I think. Yeah, because I just saw the minute go to 55. Thank you, and we'll see you in time.
So then, welcome back from the short 10-minute break. It's a pleasure to be here and to continue with Rocio's presentation where she left off. So together we've been doing quite a bit of work on regression discontinuity science for the last almost a decade now, believe it or not. And some of what we're presenting today is a summary of some of the main results that we came up with, along with some other things that we learned from other scholars along the way. And they're all summarized in this set of slides. So Rocio gave a gentle introduction to different RD designs and frameworks, and then presented quickly the idea of RD plots. And I think there is never enough emphasis in saying that those devices are extremely useful for visualization, but they can be very damaging if you try to learn something from them alone. Putting myself for a minute an econometrician hat, I should say that it's always very important to do principled estimation and inference. The RD plots are great to visualize RD designs, but they can actually be misleading in many cases. And so I'll touch base on that quite a bit for most of my presentation today. I'll try to show you how sometimes curvature of the underlying regression functions or variability of the data itself could lead to misleading conclusions, empirical conclusions, in otherwise very clean or good-looking RD designs. Great. And then she also covered the idea of local randomized experiments or local randomization in the context of RD designs. And I won't touch base on that any longer. I'll just lift a couple of ideas from that when I get to my part. And so my part is about the other approach that I think is also quite popular. And these two approaches in many ways are combined. And originally, if we were to do a history lesson, which we won't, you will recognize that these two approaches are coming together and splitting at some point from a common approach. And the common approach was all the way back. It could be found all the way back to the beginning when people were thinking about regression discontinuity science, and conceptually they were thinking of them as local randomized experiments or global even randomized experiments in some sense. And then, however, they would use arguably very parametric approaches to estimate those effects and eventually do inference on those parameters. And so these two branches of thinking about regression discontinuity science, I think both come as a response to those early approaches in the literature. The local randomization approach takes very seriously this idea of local, as if an experiment locally, and then tries to deploy ideas from analysis of experiments. And then on the other hand, the local polynomial methods come as a response to the global approaches that you would find early on in the literature. And I'll show you some examples of that as we move forward. So what is the key idea in the local polynomial approach world? Well, it is constructed from an identifying assumption, as it should be, I think. So you first think about what the parameter of interest is, and then how you can actually think of identifying it from the data. And in order to do that, you need to impose some sort of assumption, which is most likely untestable, and so it has to be believed to hold in the underlying data generating process, from which we're going to try to draw inferences. And so what is the idea in this context? Well, it's a continuity one. So RD designs from a continuity perspective are interested usually in parameters that are defined at a single point on the space of the score running variable, the score variable or the running variable. And in many cases, the most popular of those parameters is the average effect. And so the more proper way to define it will be an average treatment effect at the cutoff. And that means essentially that the parameter of interest is nothing more than the difference in average responses under treatment control, under treatment status or control status for units that happen to exhibit a score value that is equal to the cutoff point. And so in itself, this may not even be called a causal parameter by some, and we can have a long and hard philosophical discussion of whether or not this can be called a causal parameter. That may depend on your views on what causality is about and how to define causal parameters. But putting that aside for today, the key part of this slide is to argue that something that is unobservable, that is based on the underlying potential outcomes, of which only one of them we can see for any one unit, depending on whether they have scores below the cutoff or above the cutoff. That difference can be represented as something based on observable data. And so the key, going from the left to the right, the second equality, is just saying that we can represent the parameter of interest as a function or functionals of observable characteristics of the underlying data generating process that, I mean, observable or estimable, at least, identifiable characteristics of that underlying data generating process. And so we're going to be able to estimate these quantities. And what is the core idea? Well, the core idea is that if we're interested in the vertical jump, then we could, in principle, try to estimate the value of the condition expectation for the control group by estimating that regression function to the left of the cutoff, and then somehow take a limit or project it down or extrapolate it if you wish, or interpolate it depending on the values that you have in your data, but ultimately generating an estimate of the condition expectation from the left to the cutoff point. And then you will do the same from the right. You will try to estimate the regression function for the treated units, or the units who have scores above the cutoff. And then once you have a good handle on that condition expectation, then you will try to project it down or predict the value of that condition expectation at the cutoff. And so what is the core identifying assumption that is operating in the background is one of continuity. And continuity here means that in the absence of the treatment assignment rule, in the absence of the abrupt discontinuity in treatment assignment due to the RD design, you would have seen these condition expectation functions to continue in a smooth or a smooth way or continuous way, right? So what we're saying here is that in the absence of a treatment assignment due to the RD design, there should be no changes or not abrupt changes, these continuous changes in those conditional expectation functions. And if that was to be true, then we could attribute any discontinuity coming from the left and coming from the right on those conditional expectation functions to the treatment assignment, or to the treatment assigned. And so that's the core identifying assumption that will be operating in this continuity frame. So it's very different conceptually from what you would see in local randomized experiments, where the identifying assumptions not only restrict the relationship of potential outcomes with the score, but also say something about the assignment mechanism altogether. Okay, very good, awesome. So having that in place, now we can think about how to actually estimate and conduct inference on that treatment effect from a continuity or local polynomial perspective. And so in the literature, I think it is by now quite clear that global approximations are not a good idea. I think Rocio showed you this picture, which I have to show it again because it's just too cool not to show it, really. It basically says that global fits, which are actually the default in the RD plots, are certainly not the preferred method to try to infer the jump at the cutoff, right? And so the idea is I think, quite simple. What really happens is that when you try to feed a regression function using a polynomial approximation of a sufficiently high order, typically what happens is that the fit is fairly good in the center of the support, but it tends to exhibit, and this can be mathematically shown, it tends to exhibit quite a bit of variation on the tails, or in particular at the boundaries on the support, on the compact support that you're trying to estimate. In general, that would not be a big issue, but it just happened to be the case that in the regression discontinuity designs, it is the behavior of the function at the cutoff, which is from the perspective of the estimation at the boundary, is exactly the point that we care the most about. And so from that perspective, there is a clear trade-off, and again, in this case, from going from global fitting to local fitting. And so in a sense, what RD designs, modern ways of analyzing and estimating and conducting inference on RD designs, they will unavoidably search for localization. So they will try one way or another to zoom in to a neighborhood around the cutoff, discard observations away from the cutoff, and then try to do inference using only those observations, which essentially, I believe, mimics more closely the identifying assumptions that we impose in regression discontinuity designs. We cannot really say much about the distance, the vertical distance, or any kind of difference in general for the population in an RD design, but we can say something maybe for those units that are close to the cutoff instead. And so with that in mind, in local polynomial settings, usually what you do is you search for localization, and now you have a bunch of options in the way that you can do this. And so today, what I'm going to try to talk about is basically focusing on the most common approach in the literature, because I believe it is closely related to traditional regression-based analysis in applied microeconomics, with a couple of twists that we need to take into account in order to accommodate the specificity of regression discontinuity designs. And so the way that we're going to do this is basically, we're going to propose at least to first and foremost think about localization as the core argument in the analysis. And so the way we're going to do this is by first choosing a polynomial order, which I'm going to denote by P, and that will control the degree of the polynomial that we're going to use to approximate those conditional expectations. In the example here, that P would have been 4, and this fit would have been global, and then this would have been a very, very sensitive fit near the cutoff, but perhaps a good approximation of the underlying conditional expectations in the middle between 60 and 80. And so in the context of local polynomial analysis, instead, what we're going to do is we're going to choose a lower order polynomial fit and perhaps some weighting scheme that allow us to downweight observations as they are farther away from the cutoff point in the space of the score. But regardless of the weighting scheme, perhaps there's no weighting scheme, there is just a traditional least squares regression for a polynomial of order 1 or 2, that would be linear or quadratic, say. Then the key aspect of the regression discontinuity design is that we're going to force ourselves to localize. And so localization in RD designs will be controlled by a choice of bandwidth. So in the local randomization setting, instead of age, we use the notation of little w, just to mimic the edges of the window where the local randomization assumption was believed to give a good approximation to the underlying data generating process. In the context of local polynomials, we're going to use the letter h that determines, again, the distance from the cutoff that defines the region where we're going to conduct estimation and inference. And so the way that the procedure typically works is you choose the desired order of the polynomial, you choose some weighting scheme, sometimes it's called a kernel, and given these two characteristics, then you go ahead and choose a bandwidth that purposely discards a lot of observations and zooms into a nearby region of the cutoff point. And so there are different ways of choosing this bandwidth. I'm going to discuss 2 of them and their corresponding optimality properties. So as everything in econometrics and possibly in life, there is no one global optima, So everything is relative to what your beliefs are. Or in this case, in econometrics or statistics, we typically define it in terms of a risk function or a loss function. So at the end of the day, we have to set the rules of the game. You need to define what we care about. And once we care about something, we might be able to obtain an optimal choice. In general, there is no optimality that is uniformly true for everything. It's all relative to what you deem to be important for your problem. And so in the context of bandwidth selection, there are two criteria that I believe are particularly useful to think about how to select that bandwidth. One refers to a point estimation criteria, i.e. we're trying to find a bandwidth that gives us the best possible guess of what the treatment effect is in a very special sense. And the sense here will be mean square error. So for those of you who may not remember what that is just something about how good a point estimator is as metrized by the expected square difference between the point estimator and the actual target parameter, in our case, the vertical jump at a point, or the cutoff point. And so the mean square error essentially trades off bias and variance in a particular way. And so a second way of choosing the bandwidth that I'm going to talk about briefly is related to inference properties. So one could say, hold on a minute, I'm not particularly interested in developing an optimal point estimator for the RD treatment effect, although arguably that is a major goal in practice, but also I may want to ask a question, how should I choose the bandwidth if I wanted to have the best possible Gaussian or distributional approximation in order to conduct inference? And one way to answer that question is by looking at the errors that you make, but not in terms of mean square error for point estimation, but in terms of discrepancies between the sampling distribution of your statistic, typically a t-test of sorts, and its limiting distribution. And of course, as anything in life, very few things are Gaussian, but many things are called to be close to be Gaussian. And so we can metrize or characterize the discrepancy between the sampling variability or the sampling distribution, more precisely, of the statistic and its target limiting distribution, the normal distribution. And so those errors can be characterized, and not surprisingly, will also be a function of the bandwidth. And they will be a function of the bandwidth in a different way. And so you will trade off those errors in a different way, and eventually you will get a different optimal way of choosing the bandwidth. And there are many other ways to do this. Okay, great. So I'll touch base on that briefly and show you in practice how things change when you decide how to choose your bandwidth. And what are the drawbacks of shifting this as well? Once you do that, you're ready to go because you know the polynomial order, you know the weighting scheme that you decided to use. And now you can go straight ahead and choose the bandwidth. And once you have that neighborhood selected, you are ready to construct your point estimator. So again, the point estimator will estimate the regression from the left, the regression from the right, and then it will construct that jump. And that will be the point estimator that we're going to call the RD treatment effect. And then once we do that, now we have to decide how we're going to conduct inference. And hopefully we would like to use a procedure to form confidence intervals or perhaps conduct hypothesis tests that are procedures that are valid from some objective and demonstrable way. And so I'll talk about a couple of ways to do that, but they're all going to be related to an idea that Rocio and I and some of my close and amazing collaborators have put forward over the years, which is the idea of robust bias correction. And so I'll talk a little bit about how this idea comes about and why we think is a useful way of trying to understand or characterize better issues related to invalid inference that otherwise will come out if you were to apply the naive or the simplistic approaches that sometimes are seen in practice. And so I'll talk about that as I get there. Okay, so let me try to ground this idea. So now I'll go a little bit quicker so I can get to the meat of the analysis. So as I said before, we're trying to approximate regression functions from the control side and the treatment side locally. So to ground ideas, think of the most prototypical case. I would argue it should be the default in most applications. Every time I get to review a lot of RD papers, better or worse, and many of them are applied. And whenever I see that the linear fit has been excluded, I typically worry a little bit. I'm not saying that you should always use this, that you should only use this, but certainly a linear approximation is arguably a very safe first step in the analysis. And then how do you do this? Well, you choose p equal to 1, and then you select a window by choosing a bandwidth h, such that all the units to the left of the cutoff, but up to that value h, is they are in the control group, and then all the units to the right are in the treatment group. Okay, and so we're going to split that and we're going to analyze them separately from the left and from the right. And in each case, we're going to just run a least squares regression. So we're going to run a least squares regression, a weighted least squares regression from the left, and a weighted least squares regression from the right. And so here, the weights are just going to try to capture this idea that observations closer to the cutoff provide arguably more identifying assumption, whatever that means, but certainly we would like to upweight them. And then observations farther away from the cutoff, but still in the region of analysis determined by the bandwidth, they will receive relatively less weight. And so sometimes we like that idea. And so in order to do so, we can choose different weighting schemes that one could use. And so there are 3 of them that are quite popular in practice, and the 3 are plotted here, and they are arguably the most interesting ones. So the first one, which is a default from a point estimation perspective, because of its optimality properties, which is not super important today, is known as the triangular kernel. So this kernel is a weighting scheme that downweights observations as they are placed away from the cutoff in terms of their score. They are downweighted linearly, right? So you can also downweight them quadratically, and that is typically called the Epanechnikov kernel. Or we may choose not to weight or downweight observations at all, and that is typically called the uniform kernel. So the uniform kernel is going to resemble a traditional least squares regression. Whenever you use the uniform kernel, you are not weighting or downweighting or upweighting observations, all get the equal weight. All we are really doing is localizing, dropping the observations outside the neighborhood determined by the bandwidth, and literally running a least squares regression. And so you can, of course, run 2 least squares regressions, one from the left, one from the right, or you could also package all together in a single least squares regression. And the single least squares regression will simply define a dummy variable for whether or not units are above the cutoff, and then you will interact that dummy variable with the score. In this case, keep in mind, you should also weight by the weighting scheme, if there is such a weighting scheme, unless you choose a uniform kernel. And then, of course, this representation is only valid for p equal to 1. If you were to think of quadratic fitting locally, then you will still localize this way, but then you will have to add the quadratic square term and the interactions as well. Okay, very good. So once you chose those ingredients, we are ready to explain how the procedure works. I think it's fairly straightforward, so I'm going to go fairly quick. Imagine this is a true data generating process. Notice that there is a condition expectation to the left, there is a condition expectation to the right. In fact, they are continuous at the cutoff in this data generating process that we created. And importantly, they are not parallel, right? So that's something that is kind of important too. RD designs are going to give us something about what happens there at the cutoff point from a continuity perspective, or perhaps something around here if we are willing and able to apply a local randomization analysis. But certainly it will be hard to learn something about down there, right? So the power of the idea, the identification power of regression discontinuity designs is naturally local to the cutoff. And so anything that you aim to say or do beyond that point, we're going to deem, or the literature deems as extrapolation, which has a natural analog to external validity, if you wish, in the context of randomized experiments. And so RD designs are going to have high internal validity. They're going to give us a lot of information about what happens near the cutoff, but very or no information about what happens outside that region in the absence of additional assumptions. And there are quite a few different approaches out there, which I don't think today I'll have the time to touch base on. But there will be references at the end and some review articles that we are writing at the moment that will touch base on those ideas as well. Okay, great. So getting back to this, this is the regression discontinuity setting. And so this is a true underlying model, but we don't get to see that. What we get to see is data. The data in this case is plotted in red for those above the cutoff, in blue for those below. And of course, here I'm putting together the true underlying condition expectation functions as well as the data. In reality, you don't even see that. All you really see is the data. And this is a very clean, escalated example where the data is clearly separated from above and below according to the groups. In reality, this data will never be as nice as that. So just to give you an example, imagine that I wanted to plot for you the Lewis and Miller data, which is such a fantastic paper and data set for us to try crazy things on. So far, we haven't been able to break it, although we keep trying. And here is the RD plot that you will get if you were to get a bunch of beans, which effectively says plot each data as an individual dot. Right? So if we put 1,000 beans on each side, essentially each bean will contain 1 or 2 observations, maybe even less. And so this is basically a scatter plot. And now you can see that there is no clean separation as you would have hoped to see in my stylized example. Nonetheless, the question remains, is there a treatment effect, formally speaking, that we can estimate and later attach uncertainty to? Okay, great. So here's the data set in the stylized world. So how does local polynomial methods, work? Well, as I told you before, you choose a bandwidth. The bandwidth localizes, immediately removes all that data. That's gone for us. And now we're going to do the analysis only using the data inside the bandwidth region. And then the way we do it is quite simple. We run a local, perhaps, weighted least squares regression of some power p, in this case p equal to 1 is linear, and then we predict the value at the cutoff. And then we do the same from the left, and then we predict the value at the cutoff. And so here, let me pause for a minute, and again, RT designs are fundamentally identified in the limit, and therefore there is an extrapolation component that is unavoidable. In other words, at most, and typically never, you will see observations exactly at the cutoff. So you will only be able to estimate the regression functions with observations that are slightly away from the cutoff. Maybe the first observation landed right there, then right here, then here, then here. In the particular application of Lewis and Miller, by construction, there is one and only one observation at the cutoff, which is the 300th municipality that determined the cutoff itself. But other than that, all other observations are away from that point. And so it's unavoidable that we're going to estimate using data that is around here and here. And then we're going to predict essentially to the boundary of the support. And so we can digress quite a bit about whether this is extrapolation or not, and what exactly identification means in this case. This is something that we do quite commonly even in statistics or econometrics when you think about estimating functions at boundary points. If the variable, the conditioning variable is continuous, then the probability of seeing any one observation at the boundary will be 0, and in practice you will never have those observations there. So there's always a tiny little bit of extrapolation that is going on underlying any regression discontinuity design. And with that comes bias. So bias tends to be a big problem because usually you try to predict what the conditional expectation is at that point, but of course your linear approximation only does so much of a good job because it's an approximation to the true underlying conditional expectation. And so in these examples, you can see that the predicted value differs from the actual population conditional expectation value. And this vertical distance here is what we would call the bias, or the final sample bias. I mean, of course, bias is defined in terms of expectation. So at the end, this is just one realization, but the idea is the same. So essentially, there will be a vertical distance that captures this difference. And we're going to refer to this as misspecification error. It's natural, right? So we go near the cutoff, we define a region, and then we postulate that a linear regression is a good enough approximation for this underlying unknown conditional expectation that needs not to be linear at all. And so the question is, how much of a mistake are we making, right? And so intuitively, you can imagine that if you were to choose a large bandwidth and the conditional expectation exhibited enough curvature, then the linear approximation could not do a good job, right? So in this example, for instance, the conditional expectation looks like this and like this, and then because the bandwidth is quote unquote large, whatever that means, the bottom line is that you see that the linear fit would not do such a good job. If we were to shrink the bandwidth, then we would be approximating what is, by assumption, a continuous function, by identifying assumption. And therefore, in a local neighborhood, more local than H2, we would be able to do a better job. And so that's exactly the idea, right? So if we were to shrink from H2 to H1, then all of a sudden, the same linear model could do arguably a better job, hopefully a better job under some assumptions. And so this change in bias from a large bandwidth to a small bandwidth is going to play an important role in the analysis. I mean, ultimately, our methods are going to be, all models are fundamentally misspecified. And so the question is how we think about misspecification and what we do about it. And so in the context of bandwidth selection, this is very clear. If the only goal was to reduce misspecification, we would just shrink the bandwidth as much as we can. Of course, in practice, that is a naive response to the problem, because the smaller the bandwidth, the less observations we have to do the estimation. And so the price that we pay for reducing misspecification errors naturally is larger variability, and eventually inability to estimate the function at all. And so we need to trade off these two. And that's where the trade-off comes in to select the bandwidth. So we can select bandwidth based on a criteria, for example, for point estimation. That would be the idea of mean square error. And in mean square error settings, we're going to be trading off bias and variance and finding the optimal sweet spot where that bandwidth lands that give us the best trade-off between bias square and variance. And the idea here is very simple. I'll just show you a picture about it. If you choose a very small bandwidth, bias is very small, but variance is too large, we're better off by slightly increasing the bandwidth and improving on the trade-off. And then as I keep increasing the bandwidth, I'll reach my optima. And as soon as I cross that point, again, the trade-off flips and continues up, right? So the mean square error is a beautiful convex objective function that you can solve for, and under some conditions and assumptions, you can even give a fairly good characterizations of how this choice looks like. So in the case of a local polynomial regression, the choice would look like a fraction of the sample size, in particular a power of the sample size, times a constant. And the constant needs to be estimated. The estimation requires some additional steps, which are not super important for the purpose of today, but then eventually you can construct an estimator of that bandwidth. And that will be the default in the analysis. So typically you choose the bandwidth by fitting these constants and then selecting the bandwidth in a data-driven way. And that's very important, right? Because data-driven procedures take a little bit of the discretionary from the researcher away, so they reduce p-hacking, they increase transparency, and they allow for something that is fully replicable. So you don't need to start asking questions like, why do you choose a bandwidth of 5 or 10 or 15? We can start thinking about, okay, what the data is telling you about what the bandwidth should be. And of course, there is no unique bandwidth. So here I put a second bandwidth out there. This bandwidth is different. It has a different rate of convergence, i.e. a different fraction of the sample size or power of the sample size is being used. And more importantly, a different trade-off between bias and variance is being done. So in this coverage error approach, which effectively targets the best possible distributional approximation of the t-statistic distribution, sampling distribution to the Gaussian distribution in the sense of coverage error, these two are minimized, their distance is minimized by this particular choice. And here you can see that instead of trading off bias square and variance, what you trade off is bias and variance. And so again, there is no right answer. You just need to choose what you think is best for the problem at hand. Typically, the default will be to construct a point estimator that is optimal in a mean square error sense, and that will be your starting point. So many people in practice, and I would argue it's a good idea, they decide on a bandwidth for point estimation, and then they would like to keep that bandwidth fixed. Part of the reason is because then they're using the same observations both for point estimation and uncertainty quantification. The only difference is how to use them. And so that will be the procedure at the heart of the procedure that we'll discuss in a few minutes. Okay? So there are a couple of ways of doing this. I told you all this before. In practice, you're going to put hats on these things. So as you know, econometricians love to put hats on stuff, and that's kind of our job. So we just put hats on things whenever we don't know them. That means you go to the data and you get your best guess of those, and then you plug them in and you go with that. Okay. Awesome. So once you have these ingredients, we're ready to go. So how we are going to do inference here? Well, I hope it's pretty straightforward. Once you decided on how to estimate this point and this point, and notice this is just a least squares problem. So we all know our least squares very well. So we could very easily rely on traditional least squares inference to try to learn about the uncertainty on our point estimators, right? And so the typical approach here would be to form a t-test, right? A difference in means, but for the regression intercepts. And then that will put the two intercepts, which will be the treatment effect, the point estimator for the treatment effect, the vertical distance estimated. And then you will put down here the standard error of the difference. And so to the extent that this behaves like, and it does, a two-sample problem, then the variance of a difference is the sum of the variances. And so you can just plug in your preferred Eicher-Wide, robust, cluster robust, or whatever version you like to estimate the variance of the intercept from the left, the variance of the intercept from the right. You plug them in and you get yourself a great t-test statistic. And then comes the hope. The hope is that whenever you do that, that t-test statistic behaves like we know traditional least squares models or least squares problems behave. That is, the t-test enjoys a distributional approximation, which is a normal 0-1. And so if we get that, we are in business, right? And that will be what you typically appeal to every time that you use reg in Stata or LM in R. What you do is basically you postulate a linear regression model, you assume it's correctly specified, then you appeal to either finite sample or large sample distributional features, and then you just form your preferred confidence interval, which is point estimator plus minus, say, 2 times standard errors. And that will be the 95% typical confidence interval. What's the problem here? Well, the problem is one of misspecification error, right? So as I told you before, the key distinctive feature between regression discontinuity designs and traditional least squares problems would be that in regression discontinuity designs, we know that we're misspecified. Furthermore, we take advantage of the misspecification in order to construct an optimal bandwidth choice. So if you remember correctly, I said, oh, the bandwidth choice is a ratio of variance to bias. But of course, if bias was 0, then there will be no choice other than infinity. Therefore, the bandwidth will be the entire region. That makes sense, because if the model is truly linear, why would you localize at all. In practice, we don't like that. In practice, we do localize. We don't believe the regression function is linear, and therefore, we are facing a natural trade-off. If we're going to choose the bandwidth, the bias cannot be zero, but if the bias is not zero, then in general, the distribution approximation is not correct because it's not centered at zero in general. It depends on the choice of bandwidth that you decide to use. And in particular, if you were to use the mean square error choice, then you will discover that the limiting distribution exhibits a first order bias. And that postulates a challenge. Now we need to account for that bias if we want to go ahead and conduct inference. We cannot just rely on 1.96 quantiles and go ahead and use least squares methods. We cannot simultaneously choose a bandwidth for mean square error optimality and then pretend that there is no bias. We need to choose one. Either we choose the bandwidth in some other way, or we account for the bias afterwards. And so, in the proposal that we typically use and recommend, what we do is essentially to provide a bias correction that comes about for controlling for that extra misspecification error that you introduce when you use the mean square error bandwidth. And then because this misspecification error has to be estimated somehow, so you need to actually adjust the location of the confidence intervals by relocating them, their centering being relocated to a point where this bias is no longer the first order present, then that induces additional variability. And that additional variability can be accounted for. And so the procedure that we recommend and having our software implemented, typically what it does, it adjusts the location of the confidence interval and then accordingly enlarges the intervals by adding an account or trying to account for the extra variability that the bias correction estimate introduced in the first place. And so at the end of the day, the procedure will shift confidence intervals in location and in scale, right? So these confidence intervals will typically be displaced in their location and they will be enlarged by this additional variability introduced in the scale. And that doesn't mean that the confidence intervals will lead systematically to less statistical significant results, for example, because it all depends on the trade-off of the displacement to the enlargement of confidence intervals. So let me show you a couple of examples on how this works. So this picture tries to capture the idea of different possible bandwidth choices, and in particular, the mean square error optimal will lead to least squares confidence interval that by construction will have a first order bias. This is a mathematical fact. I don't think it's up for discussion in general. Of course, it can happen to be that that particular bias constant is zero at that point, in which case this would have not been well defined to begin with, other than infinity, of course. So once you have that, there is a bias that leads to over-rejection of the null hypothesis. So in practice, we will see that choosing the optimal mean square error bandwidth for point estimation in RT, and then constructing confidence intervals using least squares ideas will lead in general to misspecification in the location of the confidence intervals and over-rejection of the null hypothesis. So that means that we're going to be over-rejecting the null hypothesis of no treatment effect. And a back-of-envelope calculation tells you that the coverage that those confidence intervals will have will be roughly 82% for a 95% nominal level confidence interval. That means you're going to be rejecting roughly 10% of the time incorrectly the null hypothesis. So how do we fix that? Well, as I told you, we can recenter the confidence intervals, but then we need to enlarge them appropriately, okay? And so that's kind of the idea. And this problem might or might not be more important as you move yourself in the scale of bandwidth. If you choose a large bandwidth, large relative to the mean square error 1, then the problem will be exacerbated. More bias will kick in and further the distance in the centering of the confidence interval from the true nominal, the true population centering. If you go to the left of the mean square error, something that is called undersmoothing, then you can mitigate this problem. So you reduce the bandwidth relative to the mean square error, and eventually, if you reduce it enough, you might be able to regain nominal levels, theoretical, in large sample nominal levels that have been postulated. Of course, that implies a loss of power. So typically, as you do that, you can see the length of the confidence intervals become to larger and larger, and that is mechanical again, because the bandwidth is shrinking, less observations are available, the variance is larger, and the confidence intervals explode. Okay, great. So let me now show you this in action for 5 minutes, because I think it's cool to see how all these ideas come about. And so what I'm going to do is I'm going to try to go back to the original paper of Luger and Miller and try to replicate these results. And in particular, one thing that I love to do always when I see these papers is to say, well, in these papers, they chose a bandwidth of 9, 18, and 36. Of course, they are not to blame. They did that back in 2004. We didn't have all the theory and ideas that we have today. But nonetheless, it would be cool to ask the question, what is 9 relative to the mean square error bandwidth that you would like, you would obtain nowadays? And so we can do that. And so let me just show you an example of what that would look like. If I can find it, of course. Maybe down here. Oh, there we go. Beautiful. So the typical example would be like this. So this will be a plain vanilla estimate for the Luger and Miller data. So on the left-hand side, you have 2,400 observations. On the left, you have about 300. There is a few missing data values points there. And then the conventional here is nothing more than these pinky intervals and procedures, right? So it's a least squares approach to this problem. And then there, you see now that you have a point estimate. And because this is chosen to be mean square error optimal, that means that this point estimate is a mean square error point estimate of the RD treatment effect. Associated with it, you can construct a confidence standard error. The standard error is the straightforward least squares variance standard error. In this case, it's an Eicher-White heteroscedastic robust estimator. And then we have 2 options. We can do inference based on the least squares approach. That is the one that assumes no bias, which again, it would be inconsistent with the idea of choosing a mean square error bandwidth in the first place, but nonetheless, you can do that, I guess. And then alternatively, you can actually control for the bias correct, and then enlarge confidence intervals accordingly. And so that will be the confidence interval that comes out down here. And in this example, for instance, the p-value actually decreases. It goes from 0.046 to 0.42. That essentially means that the shifting of the confidence interval away from 0 is more than proportional, quotes and quotes, depending on the distribution, relative to the enlargement of the scale. And so in this case, the p-value actually goes down. So it's not even true, of course, that by doing this robust approach, you automatically lose significance. It really depends on the application at hand. And now, more importantly, what is 9? So as I said before, they use this 9 here. So, and they use 527 observations, right here. So what is 9 for them? And let's check. Well, here the optimal bandwidth is actually almost 7. So they are already a little bit over smooth. They have a bandwidth that is larger than the optimal bandwidth. And then that means in the picture here that if this is 7, then they're about 9. They're about there. Right? So in this example, they are a little bit away and farther out from what it would have been the optimal mean square error bandwidth in the region where the bias or misspecification error is even larger than you would expect to see. And so that's okay, that's what it is. And so we can actually replicate their results. So we could actually use 9 as they did. And so here's an example where we can just mechanically choose a bandwidth of 9 and then see what the results would look like. And now you can see that with a bandwidth of 9, the coefficient, the point estimator actually is decreased by about 10 to 15%. And that may be arguably potentially due to these misspecification errors with too large bandwidth to approximate correctly the condition expectation near the cutoff. And so, in particular, if you want to replicate their results, you will see that their result actually is a minus 1.895. In order to do that, they actually use a uniform kernel because back in the day, they were using least squares regressions with no weighting. So instead of using a triangular kernel, what they did is they did a uniform kernel. So here is the replication for them with the uniform kernel, and now you get exactly the minus 1.89. 52, which is the result reported in the QJ. And then there is some issue with the standard errors, which in the interest of time, I'm not going to touch base on today, but if you explore the code, you can play with it and get a sense of how that works. Okay, cool. So that's a short replication of that in the interest of time. And now in the last minute or two, since I started 2 minutes late, I earned my 2 minutes. I'm going to mention quickly ideas of falsification and validation. I know I'm not going to be able to cover everything here, and I knew that coming in, so I just gave you one slide of this. And the slide basically is just a reminder that regression discontinuity in science, to me at least, and one of the reasons I really liked them when I started working on them was that they were particularly good at falsifying, verifying, validating, interpreting. They have a bunch of interesting features that are unique and not necessarily portable to other observational studies methods. And in particular here I mentioned a few. So there is a very interesting way of thinking about whether there is manipulation of the units near the cutoff, right? So underlying the idea of continuity or the idea of local randomization, there is this notion that units should not be able to systematically place themselves in one treatment group or a control group by their choice. In other words, if they could systematically place their scores above the cutoff or below the cutoff, then obviously the comparability will no longer be there. And intuitively, you would expect them to be quite different between treatment and control groups. And so this idea was originally posed by more practitioners, and then later it was formalized and investigated in different ways. And so there is a very popular test, which is called the density continuity test, was proposed by Justin McCrary. And that one in particular seeks to try to check whether there is a disproportional jump in the mass of units on one side of the cutoff or the other. And so there are different ways of doing that. I'll show you a very quickly one visually because I think it's kind of cool to see. They just basically estimate the density of the score variable from the right and from the left, and they hope to see that there is no discrepancies, no surprises in terms of the number of units on either side of that cutoff. You can also look at the same idea from a binomial assignment test perspective. And so this code immediately tells you p-values for how surprising it is to see different number of units on each side of the cutoff. And then you can see very quickly the p-values are way away from any significant levels. That means that the number of observations expected to be seen on each side of the cutoff for different regions around the cutoff are roughly what you would expect to see if you were to randomly assign them. And that kind of appeals to the idea that they are not systematically placed on one side or the other. Of course, this is neither necessary nor sufficient. They could be placing themselves one side or the other, but they will do it in such a way that they're compensating the counts. And so this is just a very nice heuristic way of thinking about the problem. And then here's a list of many other ways of falsifying and investigating the validity of the design. I won't be able to touch on all of them. Let me just mention that pre-intervention covariates is a great idea. This was proposed by several people, including Lewitt and Miller. They have a great second table that I did not put here, where they check whether the treatment has any effect on outcomes or pre-intervention covariates that are deemed to not be affected by the treatment. And so that's a great check that indeed the channel of the treatment effect is coming from to the outcome that we care about and not other outcomes or pre-intervention covariates. There are many other tests that you can do. Good. So I'll stop here for the interest of time. So let me just thank not only on my behalf, but also on Rocio's, since we are sharing the slides to begin with. And let me just mention that in this website here, if you were to go there, you can actually find all kind of references that for all the stuff that we discussed today.